welcome to this session of this course. So, we have in the last class we have already seen how the system performance in an osmotic pressure control filtration can be obtained in case of ultrafiltration system, and then we have looked into the reverse osmosis nanofiltration system by replacing the definition of real retention by the solute mass flux through the porous membrane in order to connect the membrane surface concentration and the permeate concentration of the solute. So, we are then looking into the various variants of the solution diffusion model and how to include those in our calculations in order to get a system performance. So, next model, the modification will be looking into the Kedem-Katechalsky model for the RONF system for reverse osmosis and nanofiltration system. In this case, the diffusion the osmotic pressure model of the Darcy's law is modified as LP delta P minus sigma delta pi, where sigma is known as the reflection coefficient. So, one can get the expression of solvent flux as LP del P minus A sigma Cm minus Cp. So, we are assuming that pi is a linear function of concentration A times C in order to get a simplification in our calculation. So, sigma is the reflection coefficient, and then we will be using the film theory model as Cm is equal to Cp plus C naught minus Cp exponential Vw by k, and then we have the solution diffusion model that is Vw times Cp is equal to B times Cm minus Cp. So, we have three unknowns Vw, Cm and Cp. We have three independent equations involving these three parameters. Again, three equations, three unknown system. This is highly solvable. Again, by using a trial and error method, this set of equations can be solved to obtain the permeate concentration, permeate flux and membrane surface concentration. And it has to be just noted that if we are talking about a completely retentive membrane, then reflection coefficient sigma is equal to 1. We will be looking into the next variant of solution diffusion model. This is known as the modified solution diffusion model for RO, NF, and it is used sometimes for UF also. So, what is the modification? Modifications here is we are invoking a term, because if you go for a more open membrane, for example, reverse osmosis membrane is assumed to be almost an impervious membrane, and it's such a dense membrane. In case of nanofiltration, lower cutoff membranes, the pore size is increased compared to the reverse osmosis membranes. So, there are appearance of small pores into the well defined small pores inside the membrane matrix. Now, if you go for the higher cutoff of nanofiltration membrane, for example, 600, 800, 900 molecular cutoff, then the pore size of the membranes will be more, and the defined pores will be appearing more in number in the membrane matrix. So, therefore, if the defined pores will appear, then in addition to the diffusive flux of solute through the membrane, the convective flux through the membrane will be also predominant. So, later in the later molecular cutoff of nanofiltration membrane, both convective and diffusive flux will be equally important, and there will be a correction factor or modification factor will be appearing in the solution diffusion model in order to incorporate the convective flux through the membrane. So, therefore, the modified equation will be the modified solution diffusion model can be written as VW Cp is equal to beta Cm minus Cp plus 1 minus sigma VW C average. Okay. So, this is the additional term that will be taking care of the convective flux through the membrane. And what is the average C average? So, sigma is the reflection coefficient, VW is the permeate flux, C average is the average solute concentration in the membrane matrix, and C average is basically a log mean concentration difference between the Cm and Cp. So, it will be Cm minus Cp divided by ln Cm divided by Cp. So, this is a more realistic model for the solute flux through the membrane surface in case of open nanofiltration membrane or ultrafiltration membrane. So, in case of ultrafiltration membrane, the pore size is even larger, and so therefore, the convective flux will be sometimes predominant compared to the diffusive flux. So, in that case, the one has to take care of the convective flux as well. So, therefore, we can modify the solution diffusion model in this fashion, and if you really look into the calculations, you have the film theory by the solvent flux through the membrane matrix by the Darcy's law. So, that will be nothing but VW LP delta P minus sigma delta pi, and you have the film theory model for the flow through through the flow channel outside the membrane. VW is equal to K ln Cm minus Cp divided by C naught minus Cp, and delta pi can be expressed in terms of Cm and Cp. If we consider B is pi is a pi is a linear function of concentration. So, again 3 equations and 3 unknowns VW, Cm and Cp. These 3 equations, 3 unknown soil systems can be solvable, 3 equations and 3 unknown, and they can be solvable, and one can get a system prediction VW, Cp and Cm. Okay. So, these are the various variants of solution diffusion model in order to get the system performance in a very predictive mode. Only some of the parameters like LP, real retention, B, which is basically the solution constant for the solution diffusion model. These have to be estimated separately by conducting separate set of experiments, and once these are done, then if you know the operating conditions, if you know the transport coefficients, if you know the geometry and the solution properties, then one can have a system performance in a predictive mode. Next, we will be looking into the so that is all about the one dimensional film theory model for modeling the concentration, polarization and mass transfer boundary layer, and combining it with the transport processes those are occurring within the membrane surface, membrane matrix. Combination of this will be really going to the predict the performance of the system completely. Next, we will be looking into the shortcoming of one dimensional modeling or the film theory model, and then we will be adding complication to the system by considering a two dimensional model. But before that, we have to just look into the shortcomings or limitations of the one dimensional model. So, the first major limitation of the one dimensional model is the constant thickness of mass transfer boundary layer. So, as we have described earlier, is that if there is a membrane surface, there will be a development of mass transfer boundary layer over the membrane surface. Okay. And in case of film theory, we are assuming a constant thickness of the membrane surface. Now, let us look into two cases separately. We should not superpose on each of them. So, this is a constant thickness of film of solute over the membrane surface. This is case A, and in the second case there is a developing mass transfer boundary layer over the membrane surface. So, as we have seen earlier that the thickness of mass transfer boundary layer will be offering a resistance against the solvent flux. So, against the solvent flow. So, if the thickness is more, the less permeate flux we are going to get. If the thickness of mass transfer boundary layer is less, then we are going to get a higher permeate flux or the solvent flux across the membrane. So, in case of constant thickness of mass transfer boundary layer, the permeate flux we are going to get as same. We are going to get same permeate flux through the membrane as you go along the length of the module. But in case of developing mass, so actually this is a very realistic case, very unrealistic case whenever we are considering the mass thickness of the mass transfer boundary layer to be constant. Why? Because let us look into the entrance length of any boundary layer. For entrance length of a hydrodynamic boundary layer is 0.05 times Reynolds number. Okay. So, this is a case of hydrodynamic boundary layer or velocity boundary layer. Now, if you consider the equivalent diameter is in the order of millimeter and Reynolds number is in the order of 2000, so that is in the laminar, the LE. So, if it is in the order of millimeter 10 to the minus 3 meter and Reynolds number is in the order of let us say 2000, then entrance length will be order of few centimeter. So, 1 to 5 centimeter. That means, if we are considering a channel, a module which will be having a length of 1 meter, initial apart from initial 5 centimeter or 4 centimeter, the full channel will be having the fully developed hydrodynamic boundary layer or velocity boundary layer. But let us look into the entrance length for the mass transfer boundary layer. For mass transfer boundary layer, the entrance length will be LE by DE is equal to 0.05 Reynolds times Schmidt. Okay. So, what is Reynolds number? Reynolds, let us say laminar 2000, okay, and D equivalent is 1 millimeter in the order of 1 millimeter. Let us look into the Schmidt number. Schmidt number is mu by rho d. Now, in case of membrane filtration, we will be selecting solutes which will be higher pore size, larger size compared to the pore size of the membrane, so that they will be separated out of the membrane by the physical separation process. Now, let us even if you take a viscosity of water, so 10 to the minus 3 and density of water, that is 10 cube, and the diffusivity, typical diffusivity is in the order of 10 to the minus 11 to 10 to the minus 12 meter square per second. Even it is 10 to the minus 11, then the Schmidt number will be in the order of 10 to the power 5. If diffusivity is in the order of 10 to the power minus 12, then the Schmidt number will be in the order of 10 to the power 6. So, therefore, in case of membrane separation, we are talking about the solutes which will be having very high Schmidt number. If the Schmidt number is very high, and then if you really calculate the entrance length will be in the order of DE will be 1 millimeter, means 10 to the power minus 3, Schmidt number will be 10 to the power 5 or 10 to the power 6 into Reynolds number. So, it will be 10 to the power 3. So, this will be in the order of 10 to the power 5 meter. So, entrance length for the mass transfer boundary layer in a membrane channel will be very high. So, it is not that if you are considering 2 meter, 5 meter, or even 10 meter channel length or the tube length, the mass transfer boundary layer will be still developing. Now, let us look into the interpretation of developing boundary layer. If the boundary layer is developing, then at the beginning of the channel, the thickness of the boundary layer is less. So, therefore, it offers less resistance against the solvent flow. So, the solvent flux will be maximum. Okay. As the thickness increases, it offers more resistance and solvent flux is lower. So, it will be less. So, like that it will be less. So, as you go down across the channel length, and later on when it will be its growth will be almost sluggish, then you will be getting the constant value, almost constant value of permeate flux. So, at the far downstream of the channel where the growth of the mass transfer boundary layer will be almost sluggish, that means its thickness is almost equal, then you are going to get a constant thickness of the film over the membrane surface, where you are getting the constant permeate flux. But the majority of the channel length, maybe 95% of the channel length, you will be having a developing mass transfer boundary layer where the permeate flux is very, very high. So, now if you assume a constant thickness of mass transfer boundary layer is formed over the membrane surface, you will be assuming a constant permeate flux over the membrane surface. So, the excess flux due to the developing mass transfer boundary layer is already overlooked. So, therefore, if one goes for an assumption of film theory which assumes a constant thickness of film, one has to under predict or under consider the permeate flux. So, whatever the permeate flux one will be getting, that will be always less than whatever in the actual scenario. So, therefore, it is essential to go for a two-dimensional model where mass transfer boundary layer is a function of both x and y, and one will be getting an actual realistic picture for a developing mass transfer boundary layer. So, that is the first assumption. So, what is the limitation of the one-dimensional model? The limitation of the one-dimensional model is that if one adopts the one-dimensional model, then the one will be under predict the permeate flux. What will be the second assumption? The second assumption is mass transfer coefficient that we have used in one-dimensional model does not include the effects of suction. Okay. Typically, the scheduled number relations are obtained from the heat and mass transfer analogy. For example, this heat and mass transfer analogy and the heat transfer Nusselt number relations are basically for the non-porous conduit. They are all for impervious conduits. Now, in case of membrane separation system, we will be having the wall or we will be having the conduits which will be having the porous walls. So, therefore, the effects of porosity will be really dominant in some cases. For example, in case of reverse osmosis, the wall porosity will be not that much. The effect may not be very important for reverse osmosis and nanofiltration. For ultrafiltration and microfiltration, the pores are sufficiently large, and one will be the mass transfer coefficient will be a function of wall suction. In that case, the effects of wall porosity will be cannot be neglected. So, these two are the limitations of the one-dimensional film theory model for modeling the mass transfer boundary layer outside the membrane surface inside the flow channel. Now, in order to circumvent that, we will be considering a two-dimensional flow situation, flow visualization or modeling, two-dimensional flow modeling in the mass transfer boundary layer. So, we assume the boundary layer, which will be the practically the actual case, is developing over the membrane system, over the membrane channel. These y direction, these x direction. So, this is the half height of the channel. So, y is equal to h here, y is equal to 0 there, x is equal to L here, and at any point of time delta is the thickness of mass transfer boundary layer, and delta will be a function, a growing function of x. Now, let us consider a steady state laminar flow. So, let us write down the mass transfer solute balance equation within this mass transfer boundary layer and see what we get. If we write down a solute balance equation within mass transfer boundary layer, let us see what we get at the steady state. U del C del x plus V del C del y is equal to d del square C del x square plus d del square C del y square. Okay. So, first term represents the convection in the x direction, the second term reflects the convective flow in the y direction. The first term on the right hand side is the diffusive term, diffusive flux in the x direction, and this is diffusive flux in the y direction. But we already know that convection U is in the order of centimeters and V is in the order of 10 to the power minus 6. U is in the order of 1 centimeter per second, V is in the order of 10 to the power minus 5 to 10 to the power minus 6 centimeter per second. So, therefore, the convective flux in the x direction will be much dominant compared to the diffusive flux in the x direction. So, we can neglect this term compared to the convective term in the x direction. So, U del C del x plus V del C del y will be is equal to d del square C del y square. So, now let us look into the velocity profiles. So, what is U? U is equal to for a laminar flow in a rectangular channel 3 u0 by 2 1 minus h minus y divided by h square. So, we will be having a typical the parabolic velocity profile as in the laminar flow within a rectangular channel, where h is the half height and u naught is the cross sectional average velocity. So, now as we have already seen that in our case is a developed hydrodynamic boundary layer, because the entrance length required for hydrodynamic boundary layer to be completely developed is few centimeter compared to the channel length of in orders of meter. Similarly, but on the other hand, the mass transfer boundary layer will be really developing throughout the whole channel length. So, therefore, it is a case of fully developed hydrodynamic boundary layer and a developing mass transfer boundary layer. So, it is a case of fully developed hydrodynamic boundary layer and developing mass transfer boundary layer. So, now let us again go back to the geometry of the system. If you really go back to the geometry of the system, this is the channel we are considering and this is the midline of the channel, y is equal to h, this is y equal to 0, this is y equal to 2h, and membrane is placed at the bottom, and this is a completely developed hydrodynamic boundary layer, and the mass transfer boundary layer is still developing. Okay. So, beyond the concentration within the mass transfer boundary layer is changing as a function of both x and y. Beyond the mass transfer boundary layer, concentration is same, it is equal to the bulk concentration. Within the boundary layer, it is a function of x and y. So, therefore, let us our governing equation, whatever we have written of the solute mass balance equation, that is valid for solute balance equation, that is u del c del x plus v del c del y is equal to d del square c del y square, is valid for y is lying between 0 and thickness of the mass transfer boundary layer. Now, if that is the case and the velocity profile we have taken the complete velocity profile is parabolic velocity profile is 3 by 2 u naught 1 minus h minus y divided by h square of that parabolic one, we are talking of this complete velocity profile. But if you look into the mass transfer boundary layer, which is the domain of validity of this equation, we are only considering only this part of the complete velocity profile, and this part is a linear one. So, that means the mass transfer boundary layer is really very small compared to the actual dimension of the channel. So, if you look into that, the thickness of the mass transfer boundary layer can be roughly assumed, approximated by this equation. Delta by dE will be inversely proportional to the Smith number, and delta, if you talk about if you put a Smith numbers around 10 to the power 5, this will be delta by dE will be less than 0.1 or 0.01. Okay, that means in with respect to actual dimension, geometric dimension of the channel, the thickness of mass transfer boundary layer is only 1% of the whole channel length. So, therefore, we can really neglect, that means y by h is very small, and we can neglect y square by h square and higher order terms. So, if you really do that, you can expand this quadratic term, you can find out that after simplification this will becomes a linear one. You can neglect y square by h square term by opening up this square, this 1 will be cancelling out, and y square by h square can be neglected, and it will boil down to a linear velocity profile, and that will be corresponding to this figure, that the part that lies, the part of the velocity profile that lies within the mass transfer boundary layer is really a linear part of the total parabolic profile of the velocity profile. So, this linear part within the mass transfer boundary layer is replaced by this. Similarly, we can now let us look into the what is replaced by V. V is the y component velocity in mass transfer boundary layer, and we assume that and since the we have already found out that delta is much less than effective diameter or channel half height. So, therefore, the thickness of mass transfer boundary layer is probably less than 1% of the channel dimension, and it is really very small. So, in order to have a continuity, we can assume that within this small channel the y dimensional. So, this is basically V w, which will be essentially coming to the negative y direction. So, we can safely assume V is equal to minus V w, which will be basically a function of x. So, why this profile is can be a velocity profile in the y component can be assumed, because the thickness of mass transfer boundary layer is much small compared to h. So, we are assume even if there is a variation of V as a function of x and y within mass transfer boundary layer, but since the thickness of the mass transfer boundary layer is really very small, then it can be assumed that at the wall the velocity we know that it is minus V w. So, we can assume if it is really small, so everywhere it is minus V w in the channel. So, therefore, the solute balance equation is now looks like 3 u 0 y by h del c del x minus V w del c del y is equal to d del square c del y square. So, I stop in this class. In the next class, what we will be doing? We will be setting up the boundary conditions of this to solve this equation, and we will be looking into the complete solution of this equation along with its boundary condition, and how the system performance can be calculated in this case of two-dimensional analysis, and that will be giving a very realistic solution of an actual what is happening, the physical phenomena that those are happening in an actual membrane channel. Thank you very much.